Hi, my name is Jason Han and I'm a cloud advocate at Microsoft. Today I'd like to talk to you about the idea of complex systems and the problems we have when it comes to learning within them. First of all, we can think of our systems in much more of a simpler binary term by looking at them in terms of systems that we can actually understand cause and effect and those that we can't. If we keep these two binary constructs, we can look at them in terms of ordered systems and unordered systems. And from there we can go even deeper. So let's start with ordered systems. The first one I want to cover is what would be called an obvious system, also known as a simple system. And a great example of this would be a bicycle. A bicycle you can take apart, you can put back together, and it's pretty easy to understand exactly what's going on and how things work. The tires turn because the gears turn, all of that. When you start talking about a complicated system, it gets a little bit different though. Let's take that bicycle example and add combustion to it. We've put in gasoline, we've got some chemicals going on, but for the most part the mechanical parts are still there. We can take apart a motorcycle and put it back together and pretty much understand all of the cause and effect relationships. But there's also other parts of a system that we don't exactly know what's going on at all. And that's going to be part of our unordered system. It's very difficult to understand how cause and effect are related. Let's go deeper into an unordered system. If we take our same idea about a complicated system with the motorcycle, and we then add, I don't know, a road to it where there's lots of different things going on, including other vehicles, including other people, now we're starting to look at a complex system where it's very difficult to draw lines between cause and effect. And there's also what would be called the chaotic system, in which it's impossible to know or understand how things are behaving with each other. A lot of that has to do with the fact that we're building socio-technical systems. There are always people involved. Now, in a complex system, causality can only be understood in hindsight. Let's talk about an example of a complex system that I think we can all relate to, the human body. Now, within the human body, there's a lot of different specialists. We've got brain specialists, heart specialists, lung, digestive, all kinds of people know lots and lots of information about certain aspects of the human body. And the same thing can be said about software engineers and those building systems, complex systems for sure. We've got application specialists, infrastructure specialists, and lots of other people who know things about the database and the network, etc. So within each of these specialists, we've got people who understand their own areas of the system, the human body, very, very well. But we've also got generalists. We've got other people within the medical community who understand the bigger picture. They kind of see things from a different angle. And it's these generalists who understand that we're always dealing with imperfect information. If you've ever tried to, let's say, learn an instrument, let's talk about some of the requirements that come along with that. First of all, let's say you're trying to learn how to play the guitar. The moment you pick up a guitar and you start going through lessons or you sit down with your coach or your teacher, you'll realize that you can play some notes, whether you've done it before or not. But you're also going to start hitting sour notes. You're going to make mistakes. That's just part of learning. No one is ever going to pick up a guitar and immediately start playing it extremely well. It's a process that takes both success and failure. So it's through the success and failure that we actually have a feedback loop that helps us understand more about what's going on within the system. We learn from our success and we learn from our failures. And it's these setbacks that actually help us improve. In fact, they're a requirement. Now, when it comes to learning, there's a lot of challenges that we have to consider. First of all, the opportunities to learn from problems aren't going to be evenly distributed. Let's talk a little bit about that more in depth. Here we have an example of an opportunity to learn. If you start thinking about some of the things we as software engineers do on a daily basis, you can see that code commits are something we do pretty commonly. Configuration changes, although not quite as often, we do those pretty regularly as well. And the same with feature releases and incident response. They kind of decrease, but we still do them a little bit, enough to provide some opportunity to learn. Let's talk about the consequences of failure. When it comes to code commits, we do those all the time. Yet, the consequences of something going wrong when we do them are very low. And the consequences of those are a little bit less than problems with a code commit. When you do a feature release, if something goes wrong, the impact of that problem could be even bigger. And then last, if we look at incident response, if you're not able to respond to an incident and recover from problems, well, that's going to have a high impact to your business. The point I'd like to make here is that low stakes and high frequency provide high opportunity, yet high stakes and low frequency provide a low opportunity for improvement. So what that means is it's really about frequency providing the opportunity for us to learn and improve. But what do we even mean when we're talking about an incident and some sort of problem with our system? Well, for starters, incidents are subjective. If you look at the different definitions of incidents across all kinds of organizations, everyone has their own flavor. In many cases, incidents are feared and avoided, which means they're creating low opportunities to learn and improve. In my experience, preventing incidents or fearing them entirely is actually not that helpful. One of my colleagues from Microsoft had a great quote at this past Monitorama in Portland. She said, "It costs you an outage to get to that data." And she's so true. Every time there's a problem, every time there's a service disruption, there is all kinds of information, not only on what's going on with the system, but also your people about how you can learn and improve and build more reliable systems. And to label an incident as something bad is not only not truly understanding complex systems, but it's counterproductive to building reliable systems. And also, quite frankly, it's dangerous depending on the industry and the things that you're trying to build. In reality, incidents are nothing more than just a continuous feedback loop of your complex system. They are a pulse on what's going on within your infrastructure, your applications, and all of the things that are going on as part of the complex system. Okay, so let me share with you a few techniques that I think are helpful when it comes to learning. First of all, it's important that you do some sort of post-incident retrospective. Root cause analysis, although better than nothing, provides insufficient information about what's actually going on within our complex systems. If you'd like to know more about this, I wrote a book. I encourage you to go download that on post-incident reviews and what we can do to learn from those problems. Now, in a root cause analysis, in many cases, it's very common for engineers to ask a series of questions, something like 5 whys. Why did this happen? Leads us to another question. And hopefully, by the end of the exercise, we understand more of what broke and what we can do to prevent that in the future. These types of exercises actually end up feeling more like a treasure hunt than anything else. But if we start looking at what's really going on during a problem in a complex system, there's a lot more that we can uncover that only 5 questions isn't going to give us. First of all, what are the mental models of all of the people that were involved in the response? We have engineers who come in with different expertise. We have people who are part of different conversations. Not everyone shares the same tooling. Engineers will also have different theories about what's going on. They also come in with a lot different varying ideas about how the system works and what their general information and knowledge of the system. There's a lot more data that we really can be collecting about what's happening in an incident. It's not just about the technology. So if we look at this in a different angle, we've got all of these different ideas that are going through the heads of our engineers. There's technical things that we want to consider. There's procedural things that we want to consider. It actually becomes a little bit more of a mess. That's where we start thinking of things in terms of a complex system. But complexity isn't just going to exist in one person. There's many engineers who are involved in some sort of incident response. Now, when we start looking at the timeline of events, when there is a problem, we can start looking at it in a little bit different angle. We can see in this example that over time, the impact of an outage was escalating. Engineer 1 got involved, there where you see TTD, or the time to detect. Then Engineer 2 came in just a little bit later and seemingly did something that affected the impact in a positive way. Here you can see Engineer 3 and Engineer 4 show up on the scene and start doing their own efforts to try to help recover the system. And then Engineer 5 shows up. And it's at this point that we actually see the impact of the problem start to reduce. Then Engineer 6, 7, and 8 all show up to the scene to see what they can do to help with the problem as well. Now, it's very common to discuss the timeline of events and everything that was taking place, who was doing what commands were they using, what tools were they looking at, what ideas were they coming up with. and try to capture that all within a timeline so we can go back and analyze that in our retrospective analysis. But incidents aren't linear, and it's something that I think we all commonly forget. And the fact is, reality isn't linear either. So we have to start looking at our incidents in a little bit different angle. We can start to see that while Engineer 1, who was the first person on the scene and tried to do something that would recover from services, it wasn't until Engineer 5 showed up that something took place that actually improved things. But that doesn't mean Engineer 1 just disappeared. At that time, or during that entire time, they were also coming up with new theories. They were looking at what the other engineers were doing. They were asking questions. There's a lot of nuance that happens in an incident that is rarely captured in things like a root cause analysis. Now, you can start to see with all of these different engineers and all of the different things that they know and the knowledge that they have and the mental models that they come with, this is where even more complexity starts showing up inside of our incident response. And so here we can see how our treasure hunt isn't really providing enough detail, at least not enough for us to really learn and improve within the complex system. Now, a critical component of any resilient system is that we actually have ways to learn from what we would call even a near miss, something that we didn't identify as an incident. There's all kinds of things that we could learn from about how engineers actually prevented systems from going down. Rarely will you see anyone do any sort of retrospective analysis on a near miss. What we're trying to do is improve our operational knowledge and our mental models about how these complex systems work. It's through exploration and experimentation that we can actually start to make improvements with our systems, with our socio-technical systems. Now, in terms of an exploration idea, the learning reviews is what I like to suggest. This could be just sort of taking your current model, maybe that is a root cause analysis, and adding some additional questions to really get at the understanding of what our engineers were thinking and what they were doing. Really trying to pull out and extract more of what's going on in the minds of our engineers. And when we talk about experimentation, it's game day exercises or chaos engineering that allows us to really poke at the system and also poke at our procedures and our processes that the people are involved in and make sure that those things are working the way we understand them. Sometimes it requires going in and kicking the tires and trying something a little bit new to see what's going on. In terms of a learning review, the most important thing is to set the context. We're here to learn. That is the most important thing on any learning review. We are here to learn, and that needs to be established very, very early. What we're trying to do in these learning reviews is actually extract the reality of what's going on, not only with the systems and the technical aspects, but also with our engineers. When you're doing a learning review, one of the most important things that you can do is to invite a broad audience. The more perspectives you have, the more important questions are going to come up. Better questions about what's actually going on within your system. Another important aspect of a good learning review is that you allow for plenty of time for people to really understand what went wrong and what they did to recover from those problems. So it's important to spread that conversation out. Allow for some time to actually reflect and understand more about what went wrong and what went right. Also look for themes and different narratives, and of course look for different action items that you can take back out and try to improve your system. One of the other things I like to remind people is that this isn't something that just sort of happens. It takes rehearsal, it takes some practice. It takes what we call game day exercises or maybe chaos experiments. And what those exercises do is actually help us to decrease all of the blind spots within our system. It increases our observability so we know more about what's taking place. It also helps us to increase our knowledge and our mental models, which, as we discussed earlier, is exactly what we're after in these learning reviews. Thanks for watching this video. I hope you found it super insightful, and I'll see you next time.